In this diagram, you can see a continuation of the picture where it's showing two different bond angles when we have 5 electron domains. Trigonal bipyramidal, recall that we have what's called an axial position and the equatorial position. The axial positions are straight up and down. I can see a balloon up top and a balloon down below. There are 3 electron domains that position themselves around the equator, known as the equatorial position. And we can see that they take the shape of a triangle, giving us 120 degrees. And then between the axial and the equatorial would be 90. Between the top axial position and all the way down to the bottom, I would see a 180 degree from top to bottom. The trigonal bipyramidal geometry shows 2 different positions. In this example, we see phosphorus pentachloride. Phosphorus is our central atom with 1, 2, 3, 4, 5 chlorines attached to it. Phosphorus would extend its octet and create PCl5. Top to bottom are the axial positions, and there are 3 equatorial positions. Exactly 90 degrees between an axial and an equatorial, and the positions of a triangle here would be the 120 degrees. Another shot of the same thing, showing axial top and bottom with the trigonal planar here giving us those 3 equatorial positions. The next electron cloud geometry is called octahedral. We started with linear, talked about trigonal planar, tetrahedral, trigonal bipyramidal, and now we're to the 6 electron domains called the octahedral. Taking a closer look before we go into the PowerPoint, there are 3 possible molecular geometries that have the electron domain of octahedral. If all 6 of the bonding pairs are bonded back to the central atom, it will be called octahedral. If 5 of the 6 electron domains are bonded, leaving 1 unbonded, it will be called square pyramidal. And if the 6 electron domains, if 4 are bonded and 2 are unbonded, it ends up to be square planar. 3 possible molecular geometries for 1 electron domain that has octahedral shape. So when there are 6 electron groups around the central atom, and again we've expanded the octet around the central atom to create room for 6 bonded pairs, we'll see it takes the shape of octahedral geometry. All positions are equivalent and gives us a 90-degree bond angle. Putting this back on the screen, we can see between any position we would have a 90-degree bond angle. You can see, just to put this back a moment, there's 2 axial positions, top and bottom, but now I see 4 equatorial positions, making a square around that center, and a square of course has a right angle, that's a 90 degree. It would be 90 degree from an axial to an equatorial. So in any direction, a 90 degree. Although from top to bottom, the 2 axial positions would have a 180 degree bond angle. All positions are equivalent. Here's a picture of the octahedral geometry. Again, showing 6 electron domains. 2 of them are top and bottom, and 4 placed around in the equatorial position. We have an axial position and the equatorial position, creating an octahedron. A molecule such as sulfur hexafluoride, SF6, sulfur the central atom. I can see the fluorine top and bottom, and I can see 4 around the equator, the axial positions and the equatorial positions. Sulfur hexafluoride has octahedral geometry. Slide 23 shows yet another opportunity to visualize this with molecular models, looking at sulfur in the center, 2 fluorines on top, and we can see the 4 positions around the equator, sulfur hexafluoride. The actual geometry of the molecule may be different from the electron geometry. When the electron groups are attached to the atoms of different size, or when the bonding to one atom is different than the bonding to another, it'll affect the molecular geometry. And lone pairs of electrons affect molecular geometry. They occupy space at the central atom but are not seen as points in terms of molecular geometry. This slide really, in my head, just introduced the concept that we've been stating with this picture. We went through in the beginning of the PowerPoint what are called electron domains, and I just touched on the fact that the electron domain may or may not match the actual molecular geometry. The only time it does match is if all the bondings of all the electron domains are indeed bonded. So what we just introduced was the fact that the electron domain tells me how many electrons are going back to the central atom, but we also have to consider how many are bonded and how many are unbonded when we decide the molecular geometry. Here's what we're looking at, slide 25. Let me get this focused here. Carbon is the central atom. I have an electron domain heading north, one to the left and one to the right. I have 3 electron domains. Of those 3, all are bonded. I would expect, looking at my Vesper chart, a trigonal planar geometry with 120 degrees, as written earlier, for the bond angle. A 3-3-0, 3 electron domains, 3 are bonded, 0 non-bonded. But notice what's happened. We have a little bit of a difference here between the predicted 120. And here's what's happened. See this double bond from the carbon up to the oxygen? Double bonds, remember, are 2 sets of electron clouds. These literally take up more room and are going to push the hydrogen away just a little further. So the predicted bond angle of 120 expands. And the reason is this double bond, those are a lot of electrons in there needing to expand away from each other. So the moral of this story is, if I see a double bond, it's going to push down a little. We're thinking about 120. Its actual measurement's 121.9. And if I squish the hydrogen closer together, we've lost a little bit. We would have predicted 120, but it's a little smaller. Double bonds push out, and they expand just a little bit beyond the 120 we would have expected, creating a smaller bond angle between the hydrogens. Because the bonds and atom sizes are not identical in formaldehyde, the observed angles are slightly different from the ideal. If I had a central atom and it all had 3 single bonds, all created equal, I could predict with confidence 120 in each direction. It's when I have some unique bond compared to the others. A double bond is unique compared to 2 singles. It's going to push the hydrogen further or closer together, therefore decreasing the bond angle here, but increasing it here. Lone pairs of electrons do the same thing. A lone pair group occupy more space on the central atom. They're clouds of electrons. Because the electron density is exclusively on the central atom rather than on shared pairs like bonding electrons, they need more size. So the relative size of repulsive force interaction goes like this. A lone pair to lone pair is greater than a lone pair to a bonding pair, which is greater than bonding to bonding. This affects bond angles, making the bonding pair or bonding pair angle smaller than expected. Let's take a peek that way. Oops, this typed over each other. Let's suppose we have a nuclei, and we have a lone pair and a bonded pair. What we're looking at is a little different effect on the bond angle. This might be easier. Let's take a look at this picture where we actually can have something in common to look at. This is a picture of nitrogen with a perfect geometry of 109.5. And let me clarify where we're finding that. In a tetrahedral, where all 4 are bonded back, none are unbonded, we get a perfect bond angle of 109.5. In a tetrahedron, these space out with 109.5. But suppose we have a 1 unbonded pair. The lone pair of